In this section, we're going to see how the Fourier series, in addition to be written as a sum of cosines and sines, can also be written as a sum of complex exponentials. The reason that we like to use complex exponentials is because it often simplifies the algebra and calculations when analyzing a system. So you'll recall from the previous section that the sine-cosine form of the Fourier series for any periodic function has a DC component and a possibly infinite number of higher frequency components at multiples of a fundamental frequency. So we'll start with the first one here. The A of n goes with the cosine, so that's an amplitude. And the frequency will be n omega naught. So n starts at 1, which is the fundamental frequency. And then when we go to integer multiples of that frequency, we go through n periods. And we have the time variable. And then we have the sine component. So that works very well for a periodic signal that is real. And now we're going to look at a way to rearrange the terms using Euler's formula in order to get the exponential form. Certain manipulations and calculations are going to be easier in the exponential form because, just like you know from phasors and circuits, a complex value can encapsulate the magnitude and the phase of a component at a particular frequency, and therefore it simplifies some things. Now let's take a look at Euler's formula and derive some related identities from it. So we have from Euler's formula, e to the jx is equal to cosine of x plus j sine of x. And we can envision this on the unit circle in the complex plane. So there's the circle with magnitude 1. That's the locus of all the points e to the jx, where x is any real number. X is the angle in the complex plane. And let's envision e to the jx is a point right here. So that angle would be x, and the magnitude of e to the jx is 1. Now let's consider what happens when we take a point at the angle negative x, right there, negative x. So we have e to the j negative x, or e to the negative jx. And we can see from the diagram in the complex plane that these points are conjugates of each other. So they have the same real part, but the negative imaginary part. And this results from cosine and sine being even and odd functions respectively. So when I evaluate the right-hand side there, I could be substituting in negative x to the formula on top. Cosine of negative x is the same as cosine of x, since it's an even function. The real part is the same for the conjugates. But sine of negative x is negative sine of x, because the imaginary part flips for the conjugate. Now, what I do with these two equations to derive the identities I need is I'm going to add them together, and then I'm going to subtract them. So first, let's add up the two equations. Then on the left-hand side, I get e to the jx plus e to the minus jx equals twice the cosine of x. And the odd parts cancel out because I have a plus j and a minus j. So I can divide by 2, and I end up solving for cosine of x. Cosine of x is equal to e to the jx plus e to the minus jx over 2. Then I can also subtract the second form of Euler's formula from the first form of Euler's formula. So on the left-hand side, in that case, I get e to the jx minus e to the minus jx. And then on the right-hand side, I do first equation minus second. So I have cosine x minus cosine x, that term disappears, but I have j sine x minus negative j sine x. So I have 2j sine x. And I divide both sides of the equation by 2j, and I can solve it for sine of x. Now, both of these identities can be envisioned geometrically. For the first one, for the cosine, I see that I have the cosine, if I envision these complex numbers as represented by vectors in the plane here, the cosine is the sum of the vectors divided by 2. So if I use the parallelogram rule for summing vectors, I get a point right here on the real axis, which has a horizontal component of twice the cosine, and the imaginary parts cancel out. On the other hand, I can also do a geometric interpretation of the sine. Here I have vector minus vector. So I have, I now think of these as points in the complex plane, and I will have the vector from e to the minus jx to e to the jx will represent this numerator. So that vector is going vertically in the upward direction right there. And I see it is equal to twice the sine because it's the vertical component, and it's going in the vertical direction. And the horizontal component disappears. There is no horizontal component when I subtract those two. So that vertical vector is 2 sine of x in the j direction. So when I take that vector and I divide out the 2j, I have left over the sine of x. Now we're going to use these identities for cosine and sine in terms of the complex exponentials to expand this formula from the Fourier series. So I'll still have an A0 term, and then I'll have my summation from n is 1 to infinity, a of n, and I have cosine of x. So I have the cosine is this sum of complex exponentials over 2. So I'll do the over 2 right there. And the cosine is e to the jx, where x is the argument, so e to the j n omega naught t, plus e to the minus jx, plus e to the minus jx. And then I have the b component, and I'll pull the divide by 2j out in front in this case as well. So I'll have b of n over 2j, and the sine is the difference of the two exponential components. So I have e to the j x, where x is the argument of the sine, which is the same as the argument of the cosine, so n omega naught t, minus e to the minus j times n omega naught t. In the next step, I'm going to collect the positive j and the negative j terms. So on the next line, I still have a0. I still have a summation from n is 1 to infinity, but now I'm going to collect the positive j terms. So from the first half with the a, I have an a of n over 2, and from the second one, I have a b of n over 2j, or minus j b of n. I can see with this fraction here, for the imaginary part, if I multiply both the numerator and the denominator by j, I'm going to get minus b of n over 2j. So I need to put an extra minus here so that I get the positive 2 matching up with the positive 2j here. So this is the coefficient of e to the positive j n omega naught t. And then I have the negative exponent. So for that one, I'm going to have, again, a of n over 2. and I will have plus j b sub n in this case. So here I have minus b of n over 2j. And I want to get just 2, not 2j in the denominator. So I multiply by j over j. So I have minus j times b of n over 2j squared, or negative 1. So my minus 2 b of n becomes, or my minus b of n becomes plus b of n, and times j. And then my denominator becomes 2, matching up what I have here. Now, we designate these terms in the complex version, the exponential version of the Fourier series. We call the A0 term x sub 0. And we call the next term x sub n. So I have x of n is the an minus jbn over 2. And here I have x of minus n is this a plus jbn over 2. So I'm just saying that I'm introducing this new series with an x of 0 term. I have x of n, so every positive n, and I have x of minus n, so every negative subscript. And I'm saying that the value of x of n for the positive subscripted values is this function of the corresponding a of n and b of n. And also this new series I can evaluate for negative subscripts. N here is a positive number, and I take negative n. So when there's a negative subscript, I get this value here. So that is the exponential Fourier series. And I can rewrite it this way. I can say it's the sum for all n, so n is negative infinity to infinity, of x of n e to the j n omega naught t. So what have I done here? I have n is all the values from negative infinity up until infinity, all the integers. So there's a one-to-one correspondence between this line and the previous line. The x of 0 term is captured when n is 0. When n is positive, I have the 1 through infinity terms right here. And when n is positive here, I also have these terms for negative. So I've just written them as negative n, and that way I only had to write this term once. So this form of the Fourier series is very compact. It does not have 3 separate forms of terms like the sine-cosine form did. It has just one form of terms. This relationship between the sine-cosine form and the exponential form of the Fourier series. One more important point about the relationship between the exponential form and the sine-cosine form. When we look here at our x of n and our x minus n, we see they only differ by the sign of j. So that allows us to write this relationship. We can say x of n is equal to x of minus n conjugate. This applies for real signals. So if anytime you have a real signal, you can use the sine-cosine representation or the exponential representation. When you have a complex or imaginary signal, your only choice that makes sense is to use the exponential representation. In that case, this conjugate symmetry relationship, which we have just written down here, will not apply. So this relationship right here, this is called conjugate symmetry. So we're going to now do an example with this for a real signal. Is summarized in table 5.3. And we can see here down at the bottom that we have our x0 is equal to our a0, and our x of n is equal to a of n minus jb of n divided by 2, as we have just derived. We have this very simple form for the Fourier series representation of the signal x of t, which is a little easier to write than this one with the dc, the cosine, and the sine components written separately. When we want to go from exponential to cosine, we simply use this formula here in a different form. So I can see that I can find a of n is twice times the real portion of x of n, and that's when n is a positive number, and b of n is going to be negative twice the imaginary portion of x of n when n is a positive number. That's when n is positive. When n is 0, I don't have the factor of 2. I simply have x of 0 equals a of 0. Going back to the previous slide, I want to make, so let's have as given a real signal that's periodic. And we'll give some terms of its exponential Fourier series. We'll give that x of 0 is equal to 5, x of 1 is equal to 3 minus j2, x of 2 will be equal to j4. Now, since the signal is real, we know that conjugate symmetry applies. So x of minus 1 is equal to x1 conjugate, which is equal to 3 plus j2. And x of minus 2 is equal to x of 2 conjugate, is equal to minus j4. This conjugate relationship, where you can infer the x at negative indexes from those at positive indexes, only applies to real signals. Now, we'll do as a given that all other x of 0. So now what we're going to do is we can write the signal x of t using the exponential Fourier series. So exponential Fourier series is defined as the sum over all n from negative infinity to infinity of x of n e to the j n omega naught is the frequency and the time variable. And let's now go through the 5 values we have for the Fourier series. Starting with the negative 2 term, we have negative j4 e to the j times 2, negative 2, omega naught t. Then at negative 1, we have 3 plus j2 e to the negative 1j omega naught t. Then we have the term at 0, which is 5 e to the j0, which is just times 1, so that gives us our dc term. Then we have the term at 1, so 3 minus j2 e to the j times 1 omega naught t, so j omega naught t. And then finally the second harmonic, so we have the x2 term, which is j4 e to the plus j 2 omega naught t, j 2 omega naught t. Now let's convert this to the sine cosine form for comparison. So in the sine cosine form, we have a0 is equal to x0, and for the case where n is not equal to 0, we have that the x of n is equal to a minus j b for that n over 2. So now let's take a look at the n equals 1 case. We have above that x of 1 is 3 minus j2. So that tells us that we have 3 minus j2 equals a of 1 minus jb of 1 over 2. So we can see that multiplying that out, 6 minus j4 is a1 minus jb1, and as we said before, a is twice the real part, and b is negative twice the imaginary part. So b1 is 4 here. Then for n equals 2, we do the same thing, and we get a of 2 is equal to twice the real part of x2, so 0, and b of 2 is equal to negative twice the imaginary part, so negative 8. Now, these numbers allow us to write it in sine-cosine form. So x of t is also equal to a0. So we have a0, which is equal to x0, which is 5, plus, and then we have a1, so 6, and a1 goes with a cosine, so it's cosine n omega naught, so it's going to be 1 omega naught, so just omega naught t, and our b1 is 4, so plus 4 sine, same frequency, and then we have b2, so minus 8 sine, and n is 2, so n omega naught 2 omega naught t. So we see that for this real signal, which has two different frequency components, the 6 and the 4 are at the same frequency, but they add together 90 degrees out of phase. We have the corresponding signal above in complex exponential form. Now, why that is useful is because it allows us to have one term for each frequency. So these are conjugates, so I only have to know one complex number to tell me what's going on at frequency omega naught times 1. Now for this signal, I can sketch out a visual representation of these components, and these are called line spectra. And let me first do it for the sine-cosine form. So in the sine-cosine form, we have our frequency at DC omega naught 2 omega naught. And we can sketch in the magnitude. So I have at the DC, I have a magnitude of 5. At omega 1, I have 6 and 4 for my cosine and sine, and those are 90 degrees out of phase. So to get the amplitude, I have square root of 6 squared plus 4 squared. Which is about 7.2. So I have a component here, 7.2, and then at 2 I have a component that is at 8. So those are the magnitudes. And then I can also do the phase, and the tangent of the phase is going to be negative b over a, which is negative 4 over 6. But notice that that also corresponds to the angle of x1. So in this case, we have our angle 1, whether we calculate it using this inverse tangent approach, or we say it's the angle of x1, it's going to be about minus 34 degrees. And we can add that to our plot. So we have that component at omega naught. And then we do similarly for the component at twice omega naught, and that one will be plus 90 degrees. So that is the one-sided amplitude phase spectrum. We can also plot it on two sides if we are doing the exponential. So here we have omega in multiples of omega naught, so 1 and 2 minus 1 minus 2. And in this case, we work for negative ends as well. So we'll do the graph for both the amplitude and the phase. So I have my minus 34. So if that's 90 minus 90, I have my minus 34 and my plus 90. And then I have, for my negative angles, I have the conjugates. So as I'm plotting out my phase of n here, I have a positive 34 and I have a negative 90. So I have odd symmetry when I look at the x of n this way. And then I do the magnitude of the x of n. So x0 still has magnitude 5. But now my x of 1 has magnitude of square root of 3 squared plus 2 squared, or square root of 13. So that is about 3.6. So it's only half of what it was for the sine cosine form. So there's that magnitude. And x of negative 1 is just the conjugate, so it'll have the same magnitude. And then this one here at 2, at n is 2, is 4. So notice that the amplitude is split in half when I go into this exponential form. So that was that division by 2 that we got here. So that we can look at our coefficients in either form using the complex exponential or the sine cosine. These line spectra have many uses. One of them you're going to see when you take digital signal processing next term. In the laboratory, when we look at periodic signals, we can have the oscilloscope do the Fourier series calculation for us. And we will see when we input a periodic signal, we will get patterns much like these that we're looking at here. Also, we're going to see later in the chapter and in labs in digital signal processing that for signals that are not periodic, then we get a spectrum that, instead of looking like a bunch of vertical lines like this, looks more like a continuous function. So one of the things that we can see is when the spectrum appears as a series of regularly spaced lines like this, that is going to be indicating to us that we have a signal that is periodic. Another important use of these spectra is to help us visualize what sort of system or channel that we need to transmit signals like this. In this diagram here, we can see that the highest frequency is plus or minus twice the fundamental frequency. So what that means is, if we have a channel or a medium to transmit the signal on, a wireless medium or a wired medium, that, or an optical medium, for example, that we only need to be able to represent frequencies up to about twice the fundamental. If, on the other hand, we were looking at a signal that had many higher components in it, that would put additional demands on our transmission medium. So those are just a couple of the reasons that, in addition to the mathematical view of the signal, we also make these spectrum plots.